Hello, and thank you for being here. Let us gently sink into calmness as we imagine the delicate glow of stars far away and the soft, silent dance of the universe embracing us in tranquility. Imagine drifting through vast nebulae where new stars are born in clouds of stardust, feeling the slow pulse of the universe as ancient giants expand and fade. Let your mind wander to the quiet whispers of pulsars and the soft hum of distant supernova, each one a story of creation and transformation. With each breath, feel yourself floating among constellations, tracing the myths and mysteries written across the sky, allowing the vastness of space to soothe your thoughts and ease your body into relaxation. If you enjoy these relaxing moments, please consider leaving a like, subscribing, or sharing your thoughts below. Your support is deeply appreciated and helps others find their way to this peaceful space. You can also turn on the notification so you don't miss any of our future journeys. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. Stars are born in colossal clouds of gas and dust called nebulae, where gravity gradually pulls material together. Within these dense pockets, temperatures climb and pressure builds, eventually igniting nuclear fusion. This process transforms hydrogen into helium, releasing light that will shine for millions to billions of years. Some nebulae, like the Orion Nebula, glow vividly in hues of pink and red due to ionized gases. Observing a stellar nursery is like peering into a cosmic womb, where countless luminous spheres await their birth, each destined to follow a unique and fascinating journey across time and space. The earliest stars in the universe, known as Population 3 stars, formed over 13 billion years ago. Unlike modern stars, these primordial giants contained almost no heavy elements, consisting almost entirely of hydrogen and helium. Their massive sizes meant they burned intensely and lived briefly, often collapsing in violent supernova that seeded the cosmos with heavier elements. This enrichment laid the groundwork for subsequent generations of stars and planets, ultimately making life possible. Observing distant galaxies allows astronomers to glimpse echoes of these ancient stars, providing a window into the universe's earliest epochs and its chemical evolution. Red dwarfs are the most common type of star in the Milky Way, yet they often go unnoticed because of their faint luminosity. Despite their unassuming glow, they are incredibly long-lived, often persisting for tens to hundreds of billions of years, far exceeding the Sun's lifespan. These stars burn their fuel slowly and steadily, emitting steady warmth that could theoretically support life on orbiting planets. Their small size and low brightness make them difficult to detect with the naked eye, but in the grand cosmic inventory, red dwarfs quietly dominate the stellar population, a testament to endurance over flamboyance. Blue supergiants are the giants of the stellar world, radiating immense energy and burning through their fuel at staggering rates. Their brilliant blue-white light shines intensely across vast distances, illuminating the surrounding interstellar medium. However, their lives are fleeting. A star of this size may exhaust its fuel in just a few million years, culminating in a spectacular supernova explosion. Such events scatter enriched elements throughout the galaxy, contributing to the formation of new stars, planets, and eventually life. Despite their rarity, blue supergiants captivate astronomers with their size, luminosity, and dramatic yet ephemeral presence in the cosmos. Binary star systems occur when two stars orbit a shared center of mass, locked in a gravitational dance. Some binaries are wide, slowly circling one another, while others are so close that their outer atmospheres interact, exchanging material and energy. These interactions can trigger outbursts, novae, or even the formation of exotic objects like X-ray binaries and neutron stars. The diversity of binary systems offers astronomers a laboratory to study stellar evolution, mass transfer, and the extremes of gravitational physics. Observing their motion across the night sky reveals the subtle complexity underlying what might initially seem like solitary points of light. Neutron stars are extraordinary remnants of massive stars that have ended their lives in supernova explosions. Composed almost entirely of neutrons packed densely together, a neutron star condenses a solar mass into a sphere only about 20 kilometers across. Their incredible density results in a gravitational pull so intense that the fabric of spacetime itself is significantly warped. Some neutron stars rotate rapidly, emitting beams of radiation as pulsars, which can sweep across Earth with astonishing regularity. These celestial corpses offer a glimpse into physics under conditions impossible to replicate on Earth, challenging scientists' understanding of matter and gravity. A supernova is the dramatic finale of a massive star's life, where nuclear reactions collapse the core and outer layers are violently expelled. This cataclysm releases more energy in seconds than the Sun will emit in its entire lifetime. Supernovae forge heavy elements like gold and uranium, scattering them across space and enriching the interstellar medium. Some supernovae leave behind neutron stars or black holes, objects so dense that they warp space and light around them. These cosmic explosions, visible across galaxies, provide both a spectacle and a mechanism for creation, bridging the death of a star with the birth of new celestial objects. The color of a star reveals its surface temperature, with cooler stars appearing red and hotter stars shining blue or white. Our Sun, a yellow dwarf, sits in the middle of this spectrum, radiating warmth suitable for life on Earth. Stars' colors shift subtly over time as they burn fuel, swell, or cool. By analyzing stellar spectra, astronomers can determine chemical compositions, ages, and temperatures, transforming mere points of light into detailed stories of physics and history. The variety of colors in the night sky creates a celestial mosaic, each hue representing a unique phase of stellar existence. Variable stars fluctuate in brightness over time, often due to internal pulsations, eclipsing companions, or changes in energy output. Cepheid variables, for example, expand and contract rhythmically, allowing astronomers to measure distances across the cosmos with remarkable precision. Other variables, such as eruptive stars, can unpredictably brighten and fade, hinting at underlying instability. Observing these stars provides insights into the physical processes shaping stellar interiors and contributes to our understanding of cosmic distances. Their subtle rhythms or sudden flares make the night sky feel alive, a living tapestry of light pulsing across vast reaches of space. Some stars exist in star clusters, groups that share a common origin and move together through the galaxy. Open clusters, like the Pleiades, are loosely bound and contain hundreds of young stars, often enveloped in remnants of the nebula that birthed them. Globular clusters, in contrast, are tightly packed and can contain hundreds of thousands of ancient stars, relics of the galaxy's formative years. Observing clusters allows astronomers to study stellar evolution in a communal context, comparing stars of different ages and masses while enjoying a glittering spectacle of cosmic fellowship shimmering across the night sky. White dwarfs are the final stage of low to medium mass stars, remnants of once vibrant stars like the Sun. After exhausting their nuclear fuel, these stars shed outer layers, leaving behind a dense, cooling core roughly the size of Earth. Despite their small size, white dwarfs can initially be extremely hot, radiating intensely before gradually fading over billions of years. They contain no nuclear reactions, yet their residual heat shines quietly in the dark. White dwarfs may also exist in binary systems, where accretion from a companion can ignite novae or even type I supernovae, linking quiet endings with explosive beginnings elsewhere. Massive stars often create stellar winds, streams of charged particles expelled at high speeds into surrounding space. These winds can shape nebulae, sculpting intricate cavities and filaments in the interstellar medium. Over time, stellar winds contribute to the enrichment of surrounding regions, spreading elements like carbon, nitrogen, and oxygen. For massive stars, winds can be so powerful that the star gradually loses significant mass, influencing its evolution and eventual fate. The interactions of winds with nearby stars and gas create a dynamic cosmic landscape, a choreography of energy and matter playing out silently across the galaxy. Stars are governed by hydrostatic equilibrium, a balance between the inward pull of gravity and the outward pressure of nuclear fusion. This delicate equilibrium keeps stars stable for millions to billions of years. Disturbances in this balance, such as fuel exhaustion or mass accretion, trigger transformations, swelling into giants, collapsing into white dwarfs, or exploding as supernovae. Understanding hydrostatic equilibrium allows astronomers to predict lifetimes, sizes, and the ultimate fate of stars. It also explains why stars maintain their spherical shapes despite rotation or magnetic activity, a quiet testament to the harmony of forces in the heart of the cosmos. The Hertzsprung-Russell diagram is a crucial tool in astronomy, plotting stars according to luminosity and surface temperature. This chart reveals patterns in stellar evolution, showing where young stars, giants, and white dwarfs reside. By locating a star on this diagram, scientists can infer its age, composition, and potential future transformations. The diagram also highlights relationships between mass, brightness, and temperature, illustrating the underlying physics governing stellar life cycles. Through this elegant visualization, the night sky's apparent randomness becomes a map of predictable cosmic behavior, connecting the dots between countless stellar stories across the universe. Some stars rotate at astonishing speeds, completing a full spin in just hours. Rapid rotation can distort the star's shape, causing it to bulge at the equator while flattening at the poles. This rotation influences magnetic field generation, stellar wind distribution, and even surface temperature variations. Stars like Vega rotate so quickly that centrifugal forces significantly affect their structure, challenging simple models of spherical equilibrium. Observing rotation rates provides insights into angular momentum evolution and the interactions of stars with companions or surrounding disks, revealing that stellar motion is as dynamic and varied as the light they emit across the galaxy. Magnetars are a rare type of neutron star with magnetic fields trillions of times stronger than Earth's. These extraordinary fields can twist the star's crust, causing violent bursts of X-rays and gamma rays. A magnetar's magnetic strength is so intense that it can alter atomic structures nearby, influencing surrounding space. While their lifespans are short, magnetars captivate astronomers with the extremes of physics they embody, representing nature's capacity for both beauty and danger. Studying magnetars provides insights into matter under extreme conditions, the limits of magnetic phenomena, and the complex aftermath of massive stellar deaths, offering a window into the universe's wildest experiments. Stellar nucleosynthesis is the process through which stars forge elements in their cores via nuclear fusion. From hydrogen to helium, carbon, oxygen, and heavier elements, stars act as cosmic alchemists. Massive stars can synthesize elements up to iron, while supernovae and neutron star collisions produce gold, uranium, and other heavy metals. This elemental creation underpins the chemistry of planets, life, and everything in between, making stars literal forges of the universe. Understanding nucleosynthesis illuminates the origin of the elements, the life cycle of galaxies, and the interconnectedness of cosmic processes, revealing the quiet yet profound power embedded in every star's core. Pulsars are rotating neutron stars that emit beams of electromagnetic radiation at precise intervals. These cosmic lighthouses sweep across the galaxy, appearing as blinking points of light to distant observers. Their rotational periods range from milliseconds to seconds, providing astronomers with some of the most accurate natural clocks known. Pulsars have been used to detect gravitational waves indirectly, map the galaxy's interstellar medium, and test fundamental physics. The steady pulses, when observed over years, convey the intricate rhythm of the cosmos, transforming an otherwise silent universe into a structured, measurable symphony of light and time. The life expectancy of a star depends heavily on its mass. Massive stars burn brightly but die quickly, while smaller stars persist quietly for billions of years. A star 10 times the Sun's mass might live only 20 million years, ending in a spectacular supernova, whereas a red dwarf could shine for trillions of years. This relationship between mass and longevity defines the distribution of stars in the galaxy, the evolution of stellar populations, and the potential for habitable planets. In contemplating this, we realize that stars' brilliance is fleeting, yet their cumulative impact shapes the cosmos for eons. Stars often exist within galaxies, vast assemblies of hundreds of billions of stars bound together by gravity. Each galaxy has its own unique structure, from the elegant spirals of the Milky Way to the dense elliptical clusters of ancient stars. The distribution of stars within these galaxies influences their evolution, including star formation rates and the development of spiral arms or central bulges. Interactions between galaxies, such as collisions or tidal distortions, can trigger waves of starbirth, creating stellar nurseries across the cosmos. Gazing at a distant galaxy is like looking into a city of countless suns, each following its own luminous path. Some stars have exoplanets orbiting them, revealing the intricate gravitational ballet between light and matter. These planets range from gas giants many times the size of Jupiter to rocky worlds smaller than Earth. Studying these systems allows astronomers to explore planetary formation, orbital dynamics, and the potential for life beyond our solar system. Transiting planets briefly dim their host star's light, creating subtle patterns that can be detected from Earth. Each star-planet system tells a unique story, a cosmic duet of illumination and shadow, demonstrating the diverse architectures of planetary systems across the galaxy and expanding our imagination beyond the Sun's singular influence. Protostars, the earliest observable stage of stellar development, shine faintly as they accumulate mass from surrounding clouds. They are often hidden within dense dust, revealing themselves in infrared wavelengths. Gravity causes the surrounding material to collapse into a rotating disk, which may eventually form planets. Powerful jets of gas can emerge from the protostar's poles, carving cavities in the nebula. Observing protostars provides a glimpse into the delicate balance of forces shaping a star's infancy, highlighting the combination of chaos and order that allows a tiny concentration of matter to ignite into a brilliant beacon in the vast darkness of space. Stars like the Sun are classified as G-type main sequence stars, balancing energy production through hydrogen fusion with gravitational stability. Their moderate size and temperature allow for long, stable lifespans. During this phase, energy output remains relatively steady, providing a calm radiance for surrounding planetary systems. Observations of main sequence stars help astronomers understand stellar structure, energy transport, and the future evolution of our own Sun. The predictability of these stars contrasts with the drama of their massive siblings, revealing the diverse modes in which stars live, age, and influence the universe around them over billions of years. Stars interact with interstellar magnetic fields, which guide the movement of charged particles in stellar winds and influence the collapse of gas clouds into new stars. Magnetic fields can create sunspots, flares, and prominences, manifesting the complex dynamics within a star's plasma. These interactions not only affect the star's immediate environment, but also propagate outward, shaping the structure of nearby nebulae and influencing star formation. Magnetic activity varies with age, rotation, and composition, offering clues about stellar interiors. The subtle interplay of magnetic forces gives stars a dynamic personality, turning them into more than mere points of light, but active participants in cosmic processes. Some stars, known as Cepheid variables, expand and contract rhythmically, producing predictable variations in brightness. The period of their pulsation correlates with intrinsic luminosity, providing a cosmic yardstick for measuring galactic distances. By studying Cepheids, astronomers have charted the scale of the universe and determined the Hubble constant, a key factor in understanding cosmic expansion. These stars pulsate like massive cosmic metronomes, their light ebbing and flowing with remarkable regularity. Observing their cycles connects human perception with universal rhythm, offering an elegant example of how precise patterns emerge from the immense complexity of stellar physics. Wolf-Rayet stars are rare, massive stars losing mass rapidly through intense stellar winds. These winds strip away outer layers, exposing the hot, energetic core beneath, which emits ultraviolet light and sometimes produces spectacular nebular structures. Their high mass loss influences nearby star formation, enriching the surrounding medium with heavy elements. Wolf-Rayet stars often end their lives as supernovae or even gamma-ray bursts, releasing enormous energy and altering galactic environments. Observing these stars offers insight into the extreme limits of stellar evolution, showing how energy, mass, and motion combine in a luminous display of power, shaping both stars and the regions around them. Stars occasionally form in clusters, triggered by galactic collisions or shock waves from supernovae. These interactions compress interstellar gas, creating dense pockets where new stars ignite in rapid succession. The resulting starburst regions glow brilliantly, often outshining older surrounding populations. Clustered star formation demonstrates the domino effect of cosmic events, where one generation of stars can provoke the birth of another. By studying these clusters, astronomers can trace the timeline of stellar evolution, chemical enrichment, and the dynamic cycles of creation and destruction that define galaxies. The night sky becomes a layered tapestry, revealing both quiet stars and their bustling communal origins. Red supergiants represent one of the final stages for massive stars, swelling to hundreds of times the Sun's radius. Betelgeuse, a famous example, illuminates the Orion constellation with its deep reddish glow. Despite their immense size, red supergiants are relatively cool on the surface compared to smaller, hotter stars. These stars undergo complex internal mixing and core fusion processes before collapsing, often as spectacular supernovae. Observing red supergiants provides insight into the physics of massive stellar evolution, from energy transport to nucleosynthesis, and foreshadows the dramatic transformation that ultimately scatters their enriched materials into the galaxy. Stars can exist in triple or even quadruple systems, where gravitational interactions create intricate orbital patterns. Such systems challenge simplistic models of stellar dynamics, often leading to exchanges of mass, tidal distortions, or chaotic orbital shifts. Studying multiple star systems allows astronomers to probe the limits of stability and understand how stars can form and coexist in complex environments. These celestial families demonstrate that stars rarely live in isolation, and their motions, interactions, and occasional collisions shape both their evolution and the architecture of surrounding planetary systems, creating a living laboratory in the cosmos. Stars emit light across the electromagnetic spectrum, not just visible wavelengths. Infrared, ultraviolet, X-ray, and radio emissions reveal details about their temperature, magnetic activity, and interactions with surrounding matter. Observing stars in multiple wavelengths allows astronomers to detect hidden companions, circumstellar disks, and energetic phenomena invisible to the naked eye. These observations transform static points of light into dynamic, multi-layered stories, showcasing both the diversity of stellar behavior and the power of technology to expand human perception. In essence, stars shine far beyond what our eyes can see, communicating secrets across the cosmic spectrum. Planetary nebulae are created when medium-mass stars shed their outer layers late in life. The exposed core, a white dwarf, illuminates the expanding gas, forming glowing shells with intricate patterns. Colors arise from ionized elements, producing vivid blues, reds, and greens that trace chemical composition. These ephemeral nebulae last tens of thousands of years, serving as both the dying breaths of stars and the raw materials for future generations. Observing planetary nebulae connects stellar death to cosmic renewal, providing an ethereal glimpse of how stars transform matter, energy, and light into lasting, visually stunning forms. Stellar metallicity, the abundance of elements heavier than hydrogen and helium, influences a star's evolution and planet-forming potential. High metallicity stars often have planets rich in iron, silicon, and other materials necessary for rocky worlds. Low metallicity stars, conversely, may be ancient relics, providing insight into the early universe. Metallicity also affects opacity, temperature, and nuclear fusion rates within stars, subtly shaping their brightness and lifespan. By studying metallicity across populations, astronomers reconstruct galactic history, tracing how successive generations of stars enrich the cosmos with increasingly complex chemical compositions. Stars in dwarf galaxies can differ markedly from those in massive spiral galaxies, often being older, smaller, and less metal-rich. These environments offer laboratories to study primordial star formation, galactic evolution, and the effects of low-mass dynamics on stellar populations. Despite their diminutive size, dwarf galaxies contain diverse stellar systems, from ancient red giants to young luminous stars triggered by interactions with larger galaxies. Observing them reveals the variety and adaptability of star formation across environments, emphasizing that even the smallest galaxies contribute vital threads to the universe's grand stellar tapestry. Some stars rotate differentially, meaning their equator spins faster than their poles. This phenomenon influences magnetic field generation, surface temperature distribution, and stellar activity cycles. Differential rotation can lead to sunspots, flares, and even coronal mass ejections, subtly shaping the surrounding environment. By studying these variations, astronomers gain insight into the internal mechanics of stars, the transport of angular momentum, and the evolution of magnetic phenomena over time. The complexity of rotation adds texture to the otherwise seemingly uniform glow of stars, revealing hidden currents and turbulence within their luminous surfaces. Tidal interactions in close binary stars can distort shapes, induce mass transfer, and trigger energetic outbursts. In extreme cases, one star may siphon material from its companion, creating accretion disks that emit intense X-rays. These interactions accelerate evolution, producing phenomena like novae, type Ia supernovae, or exotic compact objects. Tidal forces illustrate the profound influence stars exert on one another, demonstrating that stellar life is often collaborative or competitive rather than solitary. Observing these interactions provides both dramatic spectacles and insight into the physical laws governing matter under extreme gravitational and energetic conditions. Some stars, known as carbon stars, exhibit atmospheres rich in carbon, giving them deep red hues and unique spectral signatures. These stars often expel carbon-rich dust into space, contributing to the interstellar medium and seeding future generations of stars and planets. The process of carbon enrichment occurs during late-stage fusion cycles, marking a transitional phase in stellar evolution. Observing carbon stars highlights the chemical diversity of stars, their role in cosmic recycling, and the visual spectacle created when light interacts with complex molecular clouds drifting in the galactic expanse. Wolf-Rayet binaries are especially energetic, as one star sheds mass while orbiting a massive companion. The interaction produces intense radiation, shock waves, and intricate emission lines in their spectra. Studying these systems provides insights into the evolution of massive stars, mass loss processes, and the conditions preceding supernovae or gamma-ray bursts. The luminous winds and radiation from these binaries can influence nearby star formation, enriching the environment with heavy elements while demonstrating the intertwined destinies of massive stars. In essence, they are cosmic engines, shaping both local and galactic evolution with radiant power. Some stars are gravitationally lensed by massive objects in the foreground, temporarily amplifying their brightness. This phenomenon allows astronomers to detect distant or faint stars otherwise invisible, mapping regions of space billions of light-years away. Gravitational lensing can also reveal companions, planets, or intervening dark matter structures, turning simple points of light into portals for exploration. Observing lensed stars underscores the interconnectedness of gravity, light, and geometry, showing that even stars billions of light-years distant can influence observations in our corner of the universe, bridging vast distances with subtle cosmic mechanics. Stars sometimes exhibit flares far more powerful than those seen on the Sun, particularly in young, magnetically active stars. These flares release immense energy across the electromagnetic spectrum, influencing nearby planets and potentially stripping atmospheres. Stellar flares reveal the intensity of magnetic activity, rotation, and convection within stars. By studying flare frequency and magnitude, astronomers assess habitability, stellar life cycles, and the dynamic nature of stellar surfaces. The sudden bursts of energy contrast with the slow, steady glow of most stars, reminding observers that even calm points of light can harbor sudden, dramatic outbursts of cosmic power. Many suns are surrounded by planetary systems, their gravitational influence shaping the orbits of rocky worlds, gas giants, and icy bodies. Some of these planets reside in habitable zones, where liquid water could persist if conditions align. The intricate dance of orbiting bodies, driven by gravity and angular momentum, dictates long-term stability, climate, and potential habitability. Observing these systems in distant galaxies reveals the vast diversity of planetary architectures and highlights the delicate balance that sustains life-friendly conditions. Each luminous orb becomes a central anchor, orchestrating the celestial rhythms of its companions in quiet cosmic choreography. Giant luminous spheres often undergo dramatic expansion as they age, swelling into red or orange supergiants. This inflation occurs when the core exhausts hydrogen and begins fusing heavier elements, causing outer layers to balloon. Their immense surface areas radiate light across vast distances, often dominating their local regions of the galaxy. Observing these enormous luminaries provides a glimpse into the transitional phases of stellar evolution, where stability gives way to dynamic change. Their fiery envelopes may interact with nearby interstellar gas, sculpting nebulae, enriching the environment with heavy elements and preparing for an eventual spectacular demise. In some regions, clusters of glowing suns form tight-knit associations, moving together through the galaxy like shimmering flocks. Open clusters host young, bright members still enveloped in remnants of their birth clouds, while ancient globular clusters contain densely packed, aged bodies tracing the early history of the universe. The interplay of gravity within these congregations shapes orbits, triggers occasional collisions, and influences the chemical composition of subsequent generations of objects. Witnessing these collective assemblies illuminates the social nature of luminous entities, showing how birth, life, and interaction unfold on scales, both grand and minute, across the galactic canvas. Massive blue-white beacons burn with fierce intensity, consuming fuel at extraordinary rates. Their brilliance can outshine thousands of ordinary suns, casting light far across interstellar space. Despite their splendor, their lives are brief, lasting mere millions of years before ending in violent cataclysms. These titanic objects serve as cosmic engines, forging heavy elements in their cores and spreading them through explosive deaths. Observing such luminous giants offers insight into energy transport, fusion processes, and the life cycle of the most massive inhabitants of the galaxy. Their radiant presence marks both the awe-inspiring power and fragility of celestial existence. Compact neutron remnants form when massive bodies collapse at the conclusion of their life cycles. Compressing a mass greater than the Sun into a sphere barely 20 kilometers across, these entities harbor densities so extreme that a teaspoon of their matter would weigh billions of tons. Some rotate at astonishing speeds, emitting beams of radiation detectable as pulsars across light years. Their existence demonstrates the interplay of gravity, quantum mechanics, and nuclear physics, providing laboratories for conditions impossible to replicate on Earth. Studying these remnants deepens our understanding of matter, magnetism, and the final stages of massive cosmic evolution. Binary systems reveal a mesmerizing gravitational dance, with two luminous bodies orbiting a shared center of mass. Their proximity can result in material exchange, tidal distortions, or spectacular outbursts of energy visible from afar. Some binaries emit X-rays or produce accretion disks, where matter spirals onto a dense companion, heating to extraordinary temperatures. Observing these interactions unveils the delicate balance between orbital mechanics and stellar evolution, showing how companionship can dramatically alter fate. The rhythm of this cosmic duet contrasts with the isolation of solitary bodies, demonstrating the complexity and variability of celestial lifetimes across the universe. White dwarfs mark the quiet finale of mid-sized luminaries, shrinking into dense Earth-sized remnants after shedding outer layers. Though nuclear fusion has ceased, residual heat can make them glow intensely for billions of years, slowly fading over cosmic timescales. Some exist in binary systems, where accreted material can reignite nuclear reactions, producing novae or even type Ia supernovae. These enduring cores offer insight into longevity, cooling, and the recycling of matter in galaxies. They are silent witnesses to the lives of their progenitors, preserving the history of past activity in concentrated luminous forms. Eruptive flares occasionally burst from youthful, magnetically active bodies, releasing immense energy across the electromagnetic spectrum. These events can affect orbiting worlds, stripping atmospheres, or temporarily bathing them in high-energy radiation. Such outbursts reveal the turbulent interplay between convection, rotation, and magnetic fields within luminous interiors. Observing flares informs our understanding of habitability, energy dynamics, and the life cycles of young, energetic objects. Despite their sporadic violence, these phenomena also contribute to the chemical enrichment of surrounding regions, demonstrating that even ephemeral bursts of energy can have lasting influence on a celestial neighborhood. The spectral color of a sun conveys its surface temperature, with cooler objects appearing red and hotter ones glowing blue or white. Spectroscopy reveals chemical composition, rotation, and even atmospheric turbulence, allowing astronomers to decode complex physical processes. Shifts in color or luminosity can indicate stages of evolution, companion interactions, or internal instabilities. By interpreting these variations, distant luminaries transform from static points into dynamic laboratories, conveying histories of nuclear fusion, elemental synthesis, and energy transport. A single change in hue can narrate a story spanning millions of years, connecting observers on Earth to distant cosmic phenomena. Some massive bodies lose significant mass through stellar winds, streams of charged particles expelled into surrounding space. These outflows shape nearby nebulae, sculpt cavities, and inject elements essential for future generations of celestial objects. Winds can also influence rotational dynamics and internal structures, subtly altering evolution. The continuous shedding of material demonstrates the interconnectedness of luminous entities with their environment, where energy and matter propagate outward, affecting regions light years away. Observing these currents highlights that even seemingly steady objects engage in constant exchange, transforming their surroundings while quietly participating in the ongoing cycle of cosmic creation. Variable luminaries expand and contract, pulsating in brightness over predictable cycles. Cepheid variables, in particular, act as reliable cosmic mileposts, linking luminosity to pulsation period and enabling measurements of galactic distances. Other types fluctuate irregularly, hinting at complex internal processes or surface instabilities. These oscillations create a rhythm in the cosmos, turning otherwise constant light into dynamic, measurable patterns. Observing periodicity across vast distances provides astronomers with precise tools to map the universe, understand internal physics, and reveal the hidden vitality of objects that, at first glance, may appear as simple, unchanging points of light. Nebulae surrounding luminous objects glow in vivid colors, energized by ultraviolet radiation from nearby hot bodies. Ionized gases emit blues, reds, and greens, forming intricate filaments and shells that reveal the motion, density, and composition of interstellar matter. Shockwaves from explosions or winds can further shape these clouds, producing arcs, knots, and cavities. Observing these glowing structures allows insights into the interplay between energy, matter, and gravity on a massive scale. The interplay of light and gas transforms regions of space into luminous sculptures, evoking both scientific fascination and aesthetic wonder for the observer. Red giants represent evolved luminaries in the final stages of hydrogen depletion, expanding dramatically as internal fusion shifts to heavier elements. Surface temperatures cool as the outer envelope balloons, giving these objects a characteristic reddish hue. They may lose mass through strong winds, enriching surrounding regions with carbon, nitrogen, and oxygen. Red giants often precede planetary nebula formation or supernovae, depending on mass, acting as heralds of transformation. Observing these enormous entities provides a glimpse into later life dynamics, chemical synthesis, and the delicate balance between gravity and radiation pressure as stars approach the conclusion of their life cycles. Globular clusters are tightly bound collections of ancient suns, orbiting galactic cores like dense stellar swarms. These conglomerates, sometimes containing hundreds of thousands of members, preserve the chemical signatures of the early universe. Stars within them share common ages and origins, providing astronomers with benchmarks for studying evolution and galactic history. The compact nature of globular clusters also increases gravitational interactions, creating dynamic orbits and occasional collisions. Observing these clusters gives a sense of cosmic longevity and stability, where old luminaries persist together, silently recording epochs of formation, migration, and galactic transformation over billions of years. Magnetars, highly magnetized neutron remnants, generate fields trillions of times stronger than Earth's. These magnetic behemoths occasionally erupt, emitting X-ray and gamma-ray bursts that ripple across space. Their fields distort atomic structures, and even nearby gas may be affected by these extreme forces. Studying magnetars informs researchers about fundamental physics under extraordinary conditions, including matter behavior and magnetic dynamics at unprecedented scales. Despite their rarity, they stand as examples of cosmic extremes, illustrating how the universe produces objects of unimaginable intensity, where energy, matter, and magnetic fields combine to challenge the limits of understanding. Some ancient suns display remarkably low metallicity, containing few elements heavier than hydrogen and helium. These objects, relics of early cosmic epochs, provide insight into primordial nucleosynthesis and the chemical evolution of galaxies. Their scarcity of heavy elements suggests formation before multiple generations of stellar recycling enriched the universe. Observing them offers glimpses into conditions shortly after the Big Bang, serving as living fossils that connect the present with the formative eras of galactic history. These ancient luminaries illuminate the early universe, demonstrating how chemistry, physics, and time intertwine to shape subsequent generations of celestial objects. Rapidly rotating bodies can flatten at the equator due to centrifugal force, producing an oblate shape. Rotation influences magnetic activity, surface temperature distribution, and energy output, sometimes creating equatorial bulges visible through advanced observation techniques. Extreme spin can accelerate internal mixing, alter lifetimes, and even affect the trajectory of orbiting material. Studying rotation provides insight into angular momentum evolution, binary interactions, and internal stellar dynamics. These variations remind us that seemingly uniform orbs are dynamic, complex systems, shaped not only by fusion and gravity, but also by motion and the invisible currents coursing through their interiors. Wolf-Rayet luminaries lose mass at extraordinary rates, exposing energetic cores beneath dense outer layers. Their fierce winds sculpt nearby nebulae and inject heavy elements into the interstellar medium. Often destined for supernovae or gamma-ray bursts, these entities influence surrounding star formation, chemical composition, and galactic evolution. Observing Wolf-Rayet objects provides unique insight into extreme physics, mass loss processes, and pre-explosion conditions. Their brilliant glow and turbulent surroundings highlight the universe's most energetic phenomena, offering both visual spectacle and deep scientific understanding of how matter and energy circulate on cosmic scales. Planetary nebulae, the glowing remnants of medium-sized suns, form when outer layers drift away, leaving behind a dense, hot core. Ultraviolet radiation excites surrounding gas, creating intricate shells and filaments. Colors reveal elemental composition, while shapes hint at magnetic fields, rotation, or binary companions. These ephemeral clouds enrich the galaxy with heavy elements, acting as both final statements of stellar life and raw material for future generations. Observing planetary nebulae conveys the interconnectedness of birth, evolution, and death on cosmic scales, where matter and energy continue to circulate in mesmerizing luminous forms long after the central body has ceased fusion. Some suns experience sudden outbursts known as flares, releasing tremendous energy in seconds and affecting surrounding planets. Young magnetically active luminaries often produce these intense bursts, which radiate across ultraviolet, X-ray, and radio wavelengths. These events can strip atmospheres from orbiting worlds or trigger chemical changes in their environments. Studying flares provides insight into magnetic field strength, rotational dynamics, and internal convection processes. Despite their violent nature, they also contribute to the enrichment and shaping of nearby gas clouds. Such eruptions reveal that even seemingly constant celestial objects can be unpredictable, dynamic participants in the cosmic dance of energy. Beacons of extreme mass can collapse into black holes after exhausting nuclear fuel, compressing their cores beyond the point where light can escape. The surrounding space-time warps dramatically, creating gravitational wells that bend light and matter. Accretion disks around these objects glow intensely in X-ray and gamma-ray frequencies, often producing jets of energy extending thousands of light-years. Studying these remnants illuminates the physics of gravity, matter under extreme compression, and the limits of relativity. Black holes serve as both endpoints of massive evolution and engines shaping galaxies, influencing star formation, gas flows, and the distribution of heavy elements across cosmic neighborhoods. Binary systems can display captivating interactions when one companion siphons material from its partner. Accretion disks form, heating to millions of degrees and emitting X-rays detectable across the galaxy. Occasionally, this transfer triggers novae, or even type Ia supernovae, sudden explosions that briefly outshine entire galaxies. Observing these events allows astronomers to test physics under extreme conditions and refine measurements of cosmic distances. The gravitational tug-of-war between companions demonstrates how proximity shapes evolution, mass distribution, and energy output, turning what might appear as simple points of light into complex systems of motion, fusion, and spectacular transformation. Some young luminous bodies are enveloped in protoplanetary disks, rings of gas and dust destined to form planets, moons, and asteroids. Gravitational instabilities, collisions, and accretion sculpt these disks into intricate structures. Observing them with infrared and radio telescopes reveals gaps, spirals, and asymmetries, providing a window into early planetary formation. Jets from the central object can puncture the surrounding cloud, while radiation shapes chemical reactions in the disk. Each luminous infant not only ignites nuclear fusion, but also orchestrates a miniature ecosystem of potential worlds, demonstrating how birth and creation unfold on multiple scales in a single celestial environment. Some luminous bodies exist in clusters bound together by gravity, where mutual interactions influence evolution and trajectories. Open clusters host young, bright members within the remnants of natal clouds, while globular clusters contain hundreds of thousands of older, tightly packed inhabitants. Close encounters in these dense regions can trigger collisions, tidal stripping, or orbital perturbations. Observing clustered luminaries allows astronomers to study age, composition, and the interplay of mass and motion, revealing the social dynamics of stellar populations. These assemblies transform ordinary light points into complex networks, where energy, gravity, and history intertwine over billions of years. Red supergiants expand dramatically as hydrogen in the core is depleted, inflating hundreds of times their original radius. Their surfaces cool relative to their previous phases, giving them deep crimson tones that dominate local regions of the galaxy. Massive winds drive the shedding of material, enriching the interstellar medium with carbon, nitrogen, and oxygen. These transformations precede planetary nebula formation or supernovae, depending on mass. Observing red supergiants illuminates the final chapters of stellar evolution, showing the delicate balance between radiation, gravity, and fusion. They serve as both visual spectacles and chemical forges for future generations of cosmic objects. Neutron-rich remnants can rotate astonishingly fast, sometimes hundreds of times per second, emitting beams of radiation as pulsars. Their precision rivals atomic clocks, enabling detection of gravitational waves and mapping of interstellar matter. The rotational energy slows gradually over millions of years, while magnetic fields generate complex surface phenomena. These compact bodies are laboratories for extreme physics, where density, magnetism, and relativity converge. Pulsars highlight the universe's capacity for precision amidst chaos, transforming tiny collapsed cores into cosmic lighthouses that guide astronomers across vast distances and reveal the structure and history of our galaxy. Some luminous objects have extraordinarily strong magnetic fields, distorting surface layers and triggering bursts of X-rays and gamma rays. Magnetars exemplify these extremes, with fields trillions of times stronger than Earth's. These rare entities sometimes produce giant flares visible across millions of light years. Studying their magnetism sheds light on matter under extraordinary compression and energy density, revealing limits of physics that cannot be recreated in laboratories. The violent yet transient phenomena demonstrate that the universe hosts extremes beyond imagination, where a single compact body can influence light, gas, and magnetic fields across its surrounding cosmic neighborhood. Variable luminaries pulsate in brightness due to internal instabilities or interactions with companions. Cepheid-like bodies expand and contract rhythmically, providing a direct correlation between pulsation period and intrinsic luminosity. This relation enables measurement of cosmic distances with remarkable precision. Other variables, such as eruptive or irregular types, illuminate turbulent interior processes or surface activity. Observing these rhythmic fluctuations transforms seemingly static points into dynamic storytellers, conveying both age and evolutionary stage. The predictable heartbeat of some pulsating objects turns the cosmos into a metronome, while irregular variations reveal the inherent complexity of energy transport and structural evolution in celestial interiors. Spectral analysis allows the chemical composition and temperature of a luminous body to be determined. Absorption and emission lines reveal elements present, from hydrogen and helium to heavier metals like iron, calcium, and carbon. These signatures provide insight into fusion processes, age, and surrounding environmental conditions. Shifts in lines can indicate rotation, magnetic activity, or interactions with nearby companions. Interpreting spectra transforms light into detailed narratives, decoding the physics and chemistry hidden within. From distant galaxies to local neighborhoods, spectral fingerprints allow astronomers to connect visual brightness with elemental evolution, unearthing the building blocks of planets, atmospheres, and even life itself. Planetary nebulae glow as dying luminaries expel outer envelopes, leaving behind dense, hot cores. Ultraviolet radiation excites the surrounding gas, producing elaborate shells and filamentary structures with vivid colorations. Shapes can indicate rotation, magnetic fields, or binary interactions. These ephemeral formations last tens of thousands of years, enriching space with carbon, nitrogen, and oxygen. They are simultaneously the swan song of dying suns and the seedbed for future generations of celestial objects. Observing planetary nebulae illustrates the cyclical nature of matter, the interplay between radiation and gas, and the intricate artistry of cosmic transformation in luminous death. Wolf-Rayet objects exhibit extreme mass loss, revealing searing hot cores beneath turbulent shedding envelopes. Their winds enrich interstellar regions and shape nearby gas clouds. These entities are often progenitors of supernovae or gamma-ray bursts, influencing star formation and galactic chemistry. Studying their emissions illuminates high-energy astrophysics, mass loss mechanics, and the end stages of massive evolution. The brilliant, sometimes unstable light from Wolf-Rayet objects demonstrates the energetic extremes achievable in nature and underscores the intricate feedback loops connecting individual luminaries with the broader galactic ecosystem. Ancient low-metallicity suns offer insight into the early universe, often formed before multiple cycles of chemical enrichment. Their composition provides clues about primordial nucleosynthesis and the evolution of galaxies over billions of years. Studying these relics allows astronomers to trace cosmic history, linking current populations to the first generations of luminous bodies. Their faint light carries chemical signatures, acting as fossil records that reveal the processes that gradually increased the universe's diversity of elements, setting the stage for planets, life, and the dynamic celestial landscapes observed today. Massive luminous bodies can end their lives in spectacular explosions, dispersing elements into surrounding space. Supernova remnants glow for thousands of years, sculpting interstellar clouds and triggering waves of star formation. Shock waves compress gas, while ejected heavy elements seed future generations of planets and luminaries. Observing these cosmic cataclysms provides insight into nucleosynthesis, energy dynamics, and the life cycle of matter. Despite their destructive energy, these events act as agents of renewal, transforming dying giants into creators of new structures, highlighting the interconnectedness of death and genesis on cosmic scales. Rapid rotation can induce ablateness, magnetic field variations, and enhanced mixing in mid-sized luminaries. Equatorial bulges form, altering surface temperatures and luminosity distribution. Rotation also influences the likelihood of flare activity, pulsation, or mass loss. Observing these dynamic effects allows astronomers to infer internal structure, angular momentum evolution, and the impact of rotation on life cycle stages. No two rapidly spinning objects are identical, and their complex motions reveal the subtle forces shaping energy transport, magnetic activity, and observable properties over millions to billions of years. Dwarf luminaries, small yet abundant, can live for trillions of years, far exceeding the lifespans of larger companions. They burn fuel slowly, maintaining stable luminosity over cosmic timescales. Despite their faintness, they may host orbiting planets in stable habitable zones, raising possibilities for life in environments vastly different from our solar system. Studying these diminutive yet enduring objects offers insight into longevity, energy efficiency, and the quiet persistence of low-mass bodies, demonstrating that brilliance is not always proportional to significance in shaping galactic evolution and sustaining planetary ecosystems. Tidal interactions in close systems can strip material, alter orbits, and trigger energetic events. Mass transfer can produce accretion disks, X-ray emissions, and even explosive phenomena. Observing such interactions illuminates gravitational dynamics, stellar structure responses, and high-energy astrophysics. The intricate interplay between companions transforms their evolution, demonstrating that proximity and interaction can dramatically shape outcomes over millions of years. These systems reveal the universe's capacity for complexity, where energy, matter, and gravity combine to produce dynamic behaviors unseen in isolated objects. Some massive suns produce stellar winds so powerful they carve cavities into surrounding gas clouds, shaping nebulae into dramatic arcs and filaments. These winds, traveling at millions of kilometers per hour, carry elements forged in the core outward, enriching the galaxy with carbon, nitrogen, and oxygen. The interaction with neighboring clouds can trigger bursts of new luminous objects, continuing the cycle of creation. Observing these powerful flows provides insight into mass loss mechanisms, energy transport, and the dynamic relationship between evolving luminaries and their environments, revealing that even invisible currents of gas carry the imprint of cosmic artistry. Binary companions can lock into tidal resonance, where orbital and rotational periods synchronize. This delicate equilibrium shapes mass transfer, surface heating, and internal mixing, sometimes leading to eruptive phenomena or orbital decay. Observing these interactions allows astronomers to explore gravitational dynamics, angular momentum conservation, and energy distribution under extreme conditions. In some cases, one companion may expand into a red giant and engulf its partner, producing dramatic transformations and luminous outbursts. These cosmic dances highlight that companionship profoundly influences life cycle, composition, and fate, turning otherwise solitary evolution into a complex interplay dictated by gravitational choreography over millions of years. Rogue luminous bodies drift alone through interstellar space, unbound to any galactic system. These nomads wander vast distances, invisible except for faint infrared or radio emissions. Their origins may involve ejection from binary systems or failed formation within clusters. Despite isolation, they carry insights into formation processes, mass distribution, and the variety of possible evolutionary pathways. Observing these wandering objects challenges our understanding of gravity, motion, and galactic structure. Their solitary journey contrasts with clustered populations, offering a reminder that not all luminous entities follow predictable paths, and the cosmos contains both social congregations and lone voyagers. White dwarfs in binary systems may accumulate matter from a companion, igniting surface nuclear fusion in recurring novae. These explosive events temporarily brighten the object thousands of times, sending enriched material into surrounding space. Type Ia supernovae, extreme cases of mass accumulation, serve as cosmic distance markers due to their consistent luminosity. Observing these phenomena reveals the interplay between mass, gravity, and nuclear processes. They demonstrate that even the faintest aging cores can suddenly dominate their environment, transforming from quiescent remnants into spectacular cosmic beacons and influencing galactic chemistry, structure, and the formation of future luminous generations. Some luminous bodies exist in dense clusters within molecular clouds, where ongoing formation occurs. Protobodies accumulate gas and dust from surrounding material, emitting infrared light as they contract. Jets of plasma often erupt from poles, carving out cavities and interacting with neighboring objects. Magnetic fields and turbulence influence accretion rates, while interactions among neighbors can destabilize orbits or trigger collisions. Observing these regions provides insight into early evolution, planetary system formation, and the collective behavior of nascent objects. These nurseries reveal the dramatic, chaotic beginnings of luminous life, where gravity, radiation, and motion collaborate to create future generations of cosmic luminaries. Neutron-rich remnants can emit precisely timed beams as pulsars, their rotational speed reaching hundreds of revolutions per second. The magnetic field channels radiation along the poles, producing rhythmic pulses detectable across galaxies. These objects serve as natural laboratories for physics under extreme density, magnetism, and gravitational conditions. Timing variations in pulsars allow measurement of gravitational waves, orbital parameters, and even the detection of planetary companions. Observing these compact remnants transforms tiny, collapsed objects into cosmic lighthouses, bridging vast distances and providing tools for understanding the structure, evolution, and hidden intricacies of the galactic environment. Supergiant luminous bodies often exhibit convective surfaces, where massive currents transport energy from the core outward. Granulation creates complex textures, with hot rising gas and cooler descending material producing subtle brightness variations. Observing these phenomena provides insight into energy transport, surface dynamics, and the interplay of convection, radiation, and magnetism. These massive dynamic surfaces influence the surrounding environment through winds, mass loss, and chemical enrichment. The patterns of motion, visible even from afar, illustrate the turbulence and vitality underlying seemingly constant brilliance, highlighting the complexity inherent in even the largest luminous objects in the universe. Variable giants expand and contract in response to internal pulsations, affecting luminosity and temperature. These oscillations often result from helium or hydrogen shell burning and can influence circumstellar environments, driving wind and dust formation. Observing these cycles allows astronomers to measure distances, infer internal structure, and study late-stage evolutionary processes. The rhythmic swelling and shrinking connect internal fusion processes to observable changes in brightness, revealing the intimate relationship between energy generation, structural dynamics, and interaction with the surrounding medium. Such variations turn otherwise static points of light into evolving storytellers of cosmic life cycles. Blue supergiants burn intensely, fusing heavier elements at high temperatures. Their brilliance can outshine entire clusters, while their short lifespans ensure rapid evolution. Winds and eruptions from these luminous titans enrich the interstellar medium, shaping the next generation of formation. Observing them illuminates extreme fusion processes, internal pressure balances, and the prelude to explosive death, often in the form of supernovae. Despite their fleeting existence, these massive entities play a crucial role in galactic ecology, producing elements essential for planetary systems and life, while simultaneously demonstrating the transient nature of power and energy on cosmic scales. Magnetically active youthful bodies often host circumstellar disks where planets may form. Flares, winds, and radiation interact with disk material, influencing chemical composition, disk evolution, and planet formation potential. Magnetic reconnection events may produce high-energy emissions detectable across vast distances, providing insight into early dynamical processes. Observing these environments uncovers the interaction between a central body's energy output and surrounding matter, highlighting the delicate balance necessary for stable planetary development. These early stages reveal that formation is not a solitary process, but a turbulent, energetic interplay between radiation, matter, and magnetic fields shaping future celestial systems. Red dwarfs, small and long-lived, burn fuel slowly, maintaining stable light output for trillions of years. Their low luminosity belies the potential for hosting planetary companions in habitable zones. Despite faintness, these diminutive luminaries dominate galactic populations, representing both endurance and subtle influence. Studying their activity, rotation, and flare behavior informs understanding of longevity, magnetic activity, and planetary habitability. These enduring objects demonstrate that quiet persistence can shape cosmic environments as much as brilliance, emphasizing that significance in the universe is determined by both energy output and temporal longevity across the expanse of cosmic time. Binary systems containing compact remnants can produce spectacular X-ray emissions as material falls onto a dense companion. Accretion processes heat matter to millions of degrees, creating luminous disks and often powerful jets. Observing these systems illuminates gravity's influence on energy transformation, matter behavior under extreme density, and the formation of high-energy phenomena. Variations in luminosity, spectra, or jet activity reveal dynamic interactions, showing that even small changes in mass flow can have dramatic observable consequences. These objects highlight the delicate interplay of proximity, gravity, and energy, transforming mundane companions into vivid, high-energy spectacles. Rogue planetary mass bodies drift through interstellar space, liberated from natal systems or never fully forming. Despite isolation, faint infrared emissions reveal their presence, providing insight into formation processes, mass distribution, and galactic dynamics. Studying these solitary wanderers challenges assumptions about star-planet interactions, suggesting that the cosmos contains objects in a multitude of configurations, some entirely detached from conventional systems. These nomads are living proof that formation and evolution are not limited to bound or clustered systems, offering a glimpse into the diverse pathways of luminous and subluminous bodies across the galaxy. Supernovae serve as cosmic forges, producing elements heavier than iron and dispersing them across galaxies. The explosion's shockwave compresses surrounding clouds, triggering new formation while scattering enriched material into interstellar space. Observing remnants allows reconstruction of progenitor properties, explosion dynamics, and chemical yields. These cataclysms mark both an end and a beginning, transforming massive, once brilliant bodies into sources of renewal for countless generations. They exemplify the interplay of destruction and creation on cosmic scales, where energy, matter, and light orchestrate cycles that shape galaxies, planetary systems, and the very building blocks of life. Wolf-Rayet objects often appear as luminous blue or red beacons, shedding mass rapidly through powerful winds. Their dense outflows sculpt surrounding nebulae and inject metals into the interstellar medium, preparing the environment for future generations. Often destined for supernova or gamma-ray bursts, these high-energy entities illuminate the extremes of stellar physics. Observing them provides insight into the late stages of massive evolution, revealing interactions between mass loss, radiation pressure, and rotation. Their brilliant presence demonstrates the universe's capacity for both violent transformation and the creation of conditions necessary for cosmic continuity. Ancient, low-metallicity luminaries act as living fossils, preserving chemical compositions from early cosmic epochs. Their scarcity of heavy elements reveals processes from the universe's infancy, offering clues about the first generations of formation. Observing them in globular clusters or isolated regions provides a window into galactic evolution, nucleosynthesis, and the timeline of chemical enrichment. These relics bridge present-day observations with primordial conditions, demonstrating how the universe's complexity arose gradually through successive generations of luminous objects, shaping the elemental diversity that allows planets, atmospheres, and life to exist billions of years later. Some massive luminous bodies end their lives as supernova, releasing energy that briefly outshines entire galaxies. The explosion disperses heavy elements into the surrounding medium, seeding future generations of planets and suns. Shock waves compress interstellar gas, triggering new formation events, while the remnant core may collapse into a neutron-rich object or black hole. Observing these cataclysms provides insight into nuclear fusion, stellar life cycles, and the recycling of matter across cosmic scales. Despite their violent nature, supernovae are agents of creation, transforming death into the raw material for continued evolution, illustrating the delicate interplay between destruction and cosmic renewal. Blue supergiants burn intensely, fusing elements at extreme temperatures while emitting enormous luminosity. Their short lifespans, sometimes only a few million years, contrast with the longevity of smaller bodies. Surface convection and strong winds expel material into nearby clouds, enriching the environment with metals and influencing surrounding formation. Observing these luminous titans reveals energy transport, fusion processes, and pre-supernova conditions. Despite ephemeral existence, their contribution to galactic chemistry is immense, shaping the composition of future generations. These giants exemplify the transient brilliance and profound influence of massive entities in sculpting both visible structure and elemental makeup of galaxies. Binary systems can undergo mass transfer when one companion expands and fills its Roche lobe. Material flows along gravitational contours onto the denser companion, forming hot accretion disks and sometimes producing explosive phenomena like novae or X-ray outbursts. These interactions illustrate the profound effect of proximity, tidal forces, and gravitational balance on evolution. Studying these systems illuminates energy conversion, orbital dynamics, and the eventual fate of close companions. The delicate dance of attraction, expansion, and transfer transforms ordinary binaries into high-energy laboratories, revealing how relationships between luminous entities dictate behavior, chemical enrichment, and dramatic observable events across cosmic distances. Some young luminaries remain surrounded by swirling protoplanetary disks, where gas, dust, and ice accumulate into planetary bodies. Jets and outflows puncture the surrounding clouds, sculpting cavities and redistributing material. Magnetic fields guide disk behavior, while turbulence, collisions, and angular momentum shape emerging planets. Infrared and radio observations reveal spiral structures, gaps, and asymmetries, providing clues to planet formation. These early environments demonstrate that the creation of planetary systems is inherently dynamic and interactive. Each central object not only ignites fusion, but orchestrates a miniature theatre of formation, where matter, energy, and motion collaborate to sculpt future worlds. Red giants expand as hydrogen in the core is depleted, inflating hundreds of times their original radius. Surface temperatures cool relative to earlier phases, producing deep orange or crimson tones. Massive winds carry enriched material into surrounding space, preparing the medium for subsequent generations of luminous bodies. Red giants often precede planetary nebula formation, or, if massive enough, supernovae, marking critical transitional stages. Observing them reveals the delicate equilibrium between radiation, gravity, and internal fusion, while the expelled material narrates a story of transformation. Their grandeur and influence exemplify how evolution shapes both life cycles and galactic environments over millions of years. Magnetars, highly magnetized neutron remnants, occasionally emit powerful bursts of X-rays and gamma rays. Their magnetic fields are trillions of times stronger than Earth's, distorting atomic structures and influencing nearby gas. Observing these rare entities allows study of matter under extreme pressure, density, and magnetism. Despite their rarity, magnetars illustrate the extremes possible in cosmic evolution, where a single compact object can produce energy far beyond ordinary comprehension. Their existence underscores the diversity of outcomes following massive evolution, highlighting a universe capable of producing both subtle and catastrophic phenomena in luminous remnants of collapsed progenitors. Some luminous bodies exhibit pulsations in brightness due to internal fusion cycles or surface instabilities. Cepheid variables expand and contract rhythmically, their period directly linked to intrinsic luminosity, serving as cosmic distance indicators. Irregular or eruptive variables illuminate turbulent interiors and complex structural evolution. These fluctuations transform seemingly static points into dynamic storytellers, connecting internal physics with observable phenomena. Observing pulsations provides insight into energy transport, stellar structure, and long-term evolutionary trends. The rhythmic ebb and flow of luminosity across time bridges vast distances, allowing astronomers to map both local and extragalactic structures with precision. White dwarfs are dense remnants of medium-sized bodies that have exhausted nuclear fuel. Despite their small size comparable to Earth, residual heat allows them to glow for billions of years. In binaries, accreted material can reignite fusion on the surface, producing novae or, in extreme cases, Type Ia supernovae. Studying these remnants illuminates the physics of degenerate matter, cooling processes, and long-term stellar evolution. White dwarfs represent both the quiet end of luminous life and a potential source of explosive energy, demonstrating how even seemingly inert objects continue to shape their environment across cosmic timescales. Wolf-Rayet objects shed mass at extreme rates, exposing intense, hot cores. Their winds sculpt nebulae, inject metals, and often precede supernovae. Observing them provides insight into high-energy physics, mass loss mechanics, and pre-explosion dynamics. Their brilliance and turbulence reveal the extremes of cosmic evolution, illustrating the energy and influence concentrated in the most massive objects. These entities highlight the universe's capacity for both destructive and creative processes, where explosive endings lay the groundwork for chemical enrichment and future luminous generations. Globular clusters are dense assemblies of ancient luminaries, orbiting galactic cores and preserving early chemical compositions. These systems may contain hundreds of thousands of members, tightly packed under mutual gravity. Their age and uniformity provide benchmarks for studying stellar evolution, chemical history, and galactic formation. Close encounters within clusters produce tidal interactions, collisions, and orbital reshuffling. Observing these clusters illuminates the social nature of luminous populations, showing how long-term gravitational interplay preserves structure while shaping evolution. Their compact beauty embodies both stability and dynamism, bridging cosmic history with present-day observation. Rogue objects drift unbound through interstellar space, having escaped birth clusters or never formed in conventional systems, often detectable only through faint infrared emissions. They reveal hidden populations of substellar bodies and illuminate formation processes outside bound systems. These solitary wanderers provide contrast to clustered populations, highlighting the diversity of cosmic evolution. Studying them informs theories of gravitational ejection, low mass formation, and the full spectrum of luminosity among celestial objects. Their quiet journey underscores the complexity of galactic architecture, where not all matter adheres to predictable, orbit-bound patterns. Variable giants expand and contract, influencing circumstellar environments and wind behavior. Pulsation cycles reflect shell burning and energy transport, while outer layers respond dynamically to these internal rhythms. Observing these variations allows measurement of distances, internal structure, and late-stage evolution. Such rhythmic changes link internal fusion to observable brightness, revealing that even seemingly stable bodies undergo dynamic processes. These variations create a living tapestry of light and motion, transforming the night sky into a chronicle of ongoing change across millions of years. Rapidly rotating luminaries can develop equatorial bulges, altered surface temperatures, and enhanced mixing. Angular momentum influences magnetic activity, luminosity, and structural evolution. Extreme spin may accelerate internal convection, alter lifetimes, and affect surrounding material through winds or disks. Observing rotational effects reveals the influence of motion on life cycle, energy transport, and surface dynamics. No two spinning bodies are identical, illustrating the complexity of forces shaping both internal processes and observable features, where rotation becomes a silent architect of cosmic form and evolution. Red dwarfs, diminutive but enduring, maintain steady luminosity for trillions of years. Their low energy output contrasts with larger bodies, yet their longevity ensures persistent influence in galactic populations. Many host planetary companions in stable orbits, potentially habitable, while magnetic activity and flares remain factors in planetary environments. Studying these quiet luminaries informs understanding of energy efficiency, longevity, and the subtle ways in which modest objects shape cosmic evolution. Their persistence underscores that influence is not only a function of brightness, but also time and stability across the vast expanse of the universe. Some massive suns end as supernovae, blasting energy that briefly outshines galaxies. The explosion disperses heavy elements, seeding future generations of planets and luminaries. Shockwaves compress gas clouds, triggering new formation, while the remnant core may collapse into a neutron-rich object or black hole. Observing these events reveals nuclear fusion limits, life cycles, and matter recycling on cosmic scales. Supernovae turn death into creation, transforming once luminous giants into raw material for future generations, showing the universe's balance between destruction and renewal. Blue supergiants emit immense luminosity while fusing heavy elements rapidly. Their short lifespans contrast with smaller, enduring bodies. Intense winds expel enriched material into surrounding clouds, influencing future formation. Observing these luminous titans illuminates fusion processes, energy transport, and pre-supernova conditions. Despite ephemeral existence, their influence on galactic chemistry is immense, shaping subsequent generations and planetary systems. They exemplify fleeting brilliance, demonstrating how short-lived but powerful bodies sculpt both visible structure and elemental composition across galaxies. Some compact remnants rotate at extraordinary speeds, emitting precise pulses of radiation detectable across light years. These pulsars act as cosmic clocks, with rotational precision rivaling atomic standards. Variations in timing reveal gravitational effects, planetary companions, and internal structure. Observing these dense objects transforms collapsed cores into laboratories of extreme physics, revealing matter under immense pressure, magnetic dynamics, and relativistic effects in ways impossible on Earth. Pulsars turn invisible remnants into cosmic lighthouses, guiding astronomers through the galaxy and illuminating hidden aspects of the universe. Binary systems can undergo mass transfer when one companion expands. Material flows along gravitational contours, forming accretion disks and producing novae or X-ray bursts. These interactions reveal the profound effects of tidal forces and proximity on evolution. Studying them illuminates orbital dynamics, energy conversion, and eventual fates. Close companions experience dramatic transformations, demonstrating that relationships between luminous objects dictate behavior, chemical enrichment, and observable events, turning ordinary binaries into high-energy laboratories across cosmic distances. Some young luminaries remain wrapped in protoplanetary disks, where gas, dust, and ice assemble into planets. Jets puncture clouds, while magnetic fields and turbulence shape emerging worlds. Infrared observations reveal spirals, gaps, and asymmetries, exposing early planet formation dynamics. These environments show that creation is interactive and chaotic, as central bodies orchestrate miniature systems of matter, energy, and motion. Observing them highlights how birth, radiation, and gravitational forces combine to sculpt the next generation of planets and luminaries in vivid, evolving detail. Red giants expand dramatically as hydrogen in the core depletes, cooling to deep orange or crimson hues. Winds carry enriched material outward, seeding the medium for future generations. Many precede planetary nebulae or supernova, marking critical transitional stages. Observing them reveals the balance of radiation, gravity, and fusion, while expelled matter tells a story of transformation. Their grandeur demonstrates how evolution shapes both individual life cycles and galactic environments over millions of years, illustrating the interwoven destiny of matter and energy. Magnetars, highly magnetized remnants, emit powerful X-ray and gamma-ray bursts. The magnetic fields distort matter and affect surrounding gas. Observing them illuminates matter under extreme density, pressure, and magnetism. Despite rarity, they illustrate the extremes of cosmic evolution, where a single compact object releases energy beyond comprehension. Magnetars highlight the universe's capacity for both subtle and catastrophic phenomena, showing the varied outcomes following massive evolution and the unpredictable paths of collapsed remnants. Some luminous bodies pulse in brightness due to internal fusion cycles or surface instabilities. Cepheid variables expand and contract predictably, linking period to intrinsic luminosity for cosmic distance measurement. Irregular or eruptive variations reveal internal turbulence. Observing these fluctuations transforms seemingly static points into storytellers, connecting energy generation to observable light. Their rhythmic changes provide insight into internal structure, evolution, and the dynamic interplay between fusion and surface phenomena, allowing astronomers to trace both local and extragalactic structures. White dwarfs, small and dense, glow for billions of years despite exhausting nuclear fuel. In binaries, accreted material can trigger novae, or type R supernovae. Studying these remnants reveals physics of degenerate matter, cooling, and long-term evolution. White dwarfs embody both the quiet end of luminous life and potential sources of explosive energy, demonstrating that even seemingly inert cores continue to shape their environment across cosmic timescales. Wolf-Rayet objects shed mass rapidly, revealing hot cores. Their winds sculpt nebulae and inject metals into space, often preceding supernovae. Observing them highlights high-energy physics, mass loss mechanics, and late-stage evolution. Their brilliance demonstrates the extremes of cosmic behavior, illustrating how destructive processes also prepare conditions for future luminous generations. Globular clusters contain hundreds of thousands of ancient luminaries, tightly bound by gravity. Their age and chemical uniformity provide benchmarks for evolution and galactic history. Close encounters produce collisions and orbital changes, revealing the social dynamics of clustered populations. Observing these clusters shows how gravitational interplay preserves structure while shaping life cycles, blending stability and dynamism across billions of years. Rogue objects drift alone through interstellar space, detectable primarily through faint infrared emission. These solitary wanderers may have been ejected from systems or never fully formed. Studying them illuminates formation processes and galactic dynamics, highlighting diversity in object trajectories. Their isolated journey demonstrates that not all matter adheres to predictable orbits, revealing the universe's range of possible evolutionary paths. Variable giants expand and contract, affecting circumstellar winds and environments. Pulsations reflect shell burning and energy transport, influencing outer layers. Observing these cycles allows measurement of distance, internal structure, and late-stage evolution. The rhythmic luminosity links internal fusion to observable light, transforming static appearances into living chronicles of ongoing change across cosmic timescales. Rapidly spinning luminaries develop equatorial bulges and altered surface temperatures. Angular momentum affects rotation, mixing, magnetic activity, and surrounding winds. Observing these effects reveals motion's influence on structure and energy transport. Each rotating body demonstrates the subtle forces shaping both internal and observable properties, emphasizing the universe's complexity and diversity in dynamic evolution. Red dwarfs, though small, persist for trillions of years. Their stable luminosity and long lifespans influence galactic populations, while some host planets in habitable zones. Studying them provides insight into energy efficiency, longevity, and subtle environmental influence. Their persistence shows that quiet endurance is as important as brilliance, shaping cosmic evolution across immense timescales. Some massive suns collapse after exhausting nuclear fuel, creating supernovae that scatter heavy elements into space. Shockwaves compress gas clouds, triggering new formation. The leftover core may become a neutron-rich object or black hole. Observing these events reveals fusion limits, life cycle stages, and matter recycling. Despite destruction, these explosions seed future generations, showing how death transforms into creation and sustains the ongoing evolution of galaxies and planetary systems. Blue supergiants shine intensely while fusing heavy elements, burning fuel rapidly. Their lifespans are short, but winds expel enriched material, shaping nearby clouds and influencing new formation. Observing them reveals extreme fusion processes, energy transport, and pre-supernova conditions. Despite brief existence, their influence on galactic chemistry is profound. These massive objects illustrate how fleeting brilliance can sculpt elemental composition and structure across entire galaxies. Compact remnants rotating rapidly emit precise pulses detectable across light years. Pulsars act as cosmic clocks, with timing variations revealing gravitational effects and planetary companions. Studying them uncovers extreme physics, matter under immense density, magnetic dynamics, and relativistic behavior. These collapsed cores become cosmic lighthouses, guiding astronomers through galactic landscapes and illuminating hidden processes in some of the universe's most extraordinary objects. Binary systems experience mass transfer when one companion expands. Matter flows onto the denser partner, forming hot accretion disks and sometimes triggering novae or X-ray bursts. These interactions highlight gravitational influence, orbital dynamics, and energy conversion. Studying them demonstrates how close companions reshape each other's evolution, creating high-energy phenomena observable across vast distances. Some young luminaries are surrounded by protoplanetary disks, where gas and dust assemble into planets. Jets carve cavities, while magnetic fields and turbulence shape formation. Infrared observations reveal spirals and gaps, showing early planetary system dynamics. These nurseries demonstrate that creation is interactive and chaotic, with central bodies orchestrating matter, energy, and motion to sculpt future worlds in vivid detail. Red giants expand as core hydrogen depletes, cooling to deep red hues. Strong winds eject enriched material, seeding the medium for future formation. Many precede planetary nebulae or supernovae, marking transitional phases. Observing them shows the balance between fusion, radiation, and gravity, highlighting the transformative influence these aging bodies have on galactic environments over millions of years. Magnetars, extremely magnetized remnants, occasionally erupt with X-ray or gamma-ray bursts. Their intense fields affect matter and surrounding gas. Observing them reveals matter under extreme pressure and magnetism. Though rare, they illustrate the universe's capacity for both subtle and catastrophic phenomena, showing the variety of outcomes following massive evolution and the extremes possible in compact remnants. Variable luminous bodies pulse due to internal cycles or surface instabilities. Sulfide-like objects expand and contract predictably, linking period to intrinsic luminosity, useful for distance measurement. Irregular fluctuations reveal turbulent interiors. Observing these changes transforms static points into storytellers, connecting internal energy with visible light and tracing both local and galactic structures across cosmic distances. White dwarfs, dense remnants of medium-sized bodies, glow for billions of years despite exhausted fuel. In binaries, accretion may trigger novae or type Ia supernovae. Studying them reveals degenerate matter physics, cooling, and long-term evolution. White dwarfs show how even seemingly inert remnants can influence their surroundings over vast timescales. Globular clusters contain tightly bound ancient luminaries, often numbering hundreds of thousands. Age and chemical uniformity provide insights into evolution and galactic history. Close encounters cause collisions and orbital shifts. Observing these clusters reveals how gravitational interplay preserves structure while shaping life cycles, blending stability and dynamism over billions of years. Rogue objects drift alone through space, detectable mostly via faint infrared emissions. Ejected or never fully formed, they illuminate formation processes and galactic dynamics. These solitary wanderers highlight diverse trajectories and show not all matter follows predictable orbits, emphasizing the universe's variety of evolutionary paths. Rapidly spinning bodies develop equatorial bulges and altered surface temperatures. Rotation affects internal mixing, magnetic activity, and energy distribution. Observing these effects reveals motion's influence on structure and evolution, demonstrating the universe's dynamic complexity. Red dwarfs, small but long-lived, maintain steady light output for trillions of years. Many host planets in habitable zones. Their persistence shows that influence comes from longevity as much as brightness, subtly shaping galactic environments over immense timescales. Some massive suns collapse into supernovae, scattering elements into space. Shockwaves compress nearby clouds, triggering new formation. The leftover core may become a neutron-rich object or black hole. Observing these events reveals fusion limits, life cycle stages, and cosmic recycling. Despite destruction, supernovae provide material for future generations, showing how endings create beginnings in a cycle of renewal across galaxies and planetary systems. Blue supergiants shine intensely while fusing heavy elements rapidly. Their lifespans are brief, yet winds expel enriched material into surrounding clouds. These massive objects shape galactic chemistry, influencing future formation. Observing them reveals extreme fusion processes, energy transport, and pre-supernova conditions. Despite short existence, their impact is profound, showing how fleeting brilliance can sculpt elemental composition and structure across vast cosmic scales. Rapidly rotating remnants emit precise radiation pulses detectable across light years. Pulsars act as cosmic clocks, with timing variations revealing gravitational effects and planetary companions. Studying them uncovers matter under immense density, magnetic dynamics, and relativistic behavior. These collapsed cores serve as lighthouses, guiding astronomers and illuminating hidden processes in some of the universe's most extreme and extraordinary objects. Binary systems experience mass transfer when one companion expands. Matter flows onto the denser partner, forming accretion disks and sometimes triggering novae or X-ray bursts. These interactions highlight gravitational influence, orbital dynamics, and energy conversion. Studying them shows how proximity transforms ordinary binaries into high-energy laboratories across vast distances. Young luminous bodies often remain wrapped in protoplanetary disks, where dust and gas assemble into planets. Jets carve cavities, while turbulence and magnetic fields shape formation. Infrared observations reveal spirals and gaps, showing early planetary system dynamics. These nurseries demonstrate that creation is interactive and chaotic, as central bodies orchestrate matter, energy, and motion to sculpt future worlds. Red giants swell as core hydrogen is depleted, cooling to deep red tones. Winds eject enriched material, preparing the medium for future formation. Many precede planetary nebulae or supernovae, marking transitional phases. Observing them reveals the balance of fusion, gravity, and radiation, highlighting the transformative influence these aging bodies exert over galactic environments. Magnetars, extremely magnetized remnants, release occasional X-ray and gamma-ray bursts. Their intense magnetic fields affect surrounding matter. Observing them reveals matter under extreme pressure and magnetism. Rare, yet powerful, they show how compact objects can produce both subtle and catastrophic cosmic effects, demonstrating the extremes possible in the universe's compact remnants. Variable luminous objects pulse from internal cycles or surface instabilities. Cepheid-like objects expand and contract predictably, linking period to intrinsic luminosity, essential for distance measurement. Irregular fluctuations reveal turbulent interiors. Observing these variations transforms static points into storytellers, connecting internal energy with visible light across galactic scales. White dwarfs, dense remnants, glow for billions of years after fuel exhaustion. In binaries, accreted matter may trigger novae or type Ia supernovae. Studying them reveals degenerate matter physics, cooling, and long-term evolution. They demonstrate that even quiet remnants can shape surroundings over vast timescales. As our journey through the silent beauty of distant stars comes to a close, allow yourself to sink even deeper into relaxation. Feel the gentle glow of starlight wrapping around you, the calm rhythm of cosmic winds lulling your mind, and the quiet brilliance of nebulae filling you with serenity. Let your thoughts drift like dust in the galaxy, your muscles soften, and your breath flow naturally and effortlessly. Rest here, fully supported in this safe and serene space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turn on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.